Hello. Okay, so this talk is going to be completely packed with content, maybe not people, but that's okay because I wouldn't expect that. It's much more about the content than it is about the talk. A little bit about me is that I used to make a lot of YouTube videos, and I think a lot of people around here know me from the YouTube videos, but I haven't had as much time to post the videos of what I'm working on, but I'm still very active doing lots of projects. I'm very active on GitHub. I post a lot of stuff to Twitter and Blue Sky. I have a Discord where a lot of the work on this gets done. So if you're interested to tag along, or if you have questions, or if you want to get into any of this, hit me up after this, and I can give you a Discord invite. And just personally, so even though like very few of my friends are Christian, it is my faith that like drives me to really want to see other people flourish. Like that's really what changed in my life, to want me to see others flourish even more in what they hope to do. So the structure of this talk is, number one, I'm going to give a little bit of the story behind this SDK called CH32Fun, or I guess the original name was CH32V003Fun. I'm going to say a little bit about why I think abstractions really matter and why you should think about them. And then I'm going to spend the second half of the talk going through literally every single thing that you need to do if you want to do everything I did from the ground up for your own purposes. So if you guys are ready for it, we'll see how this goes. So CH32Fun originally started as this funny little SDK for this funny little 10-cent microcontroller called the CH32V003. It's RISC-V, it's got a bunch of neat stuff. It just kind of felt like an AVR. It feels like the next, to me at least, the logical like progression of where AVRs were going. And I really just thought it was cool. And so I just decided, I was like, okay, well, I want to use this, but the existing SDK was in Eclipse at the time, and it's really janky, and I was like, okay, well, what if I just do it from the ground up? I've done this before. It's not my first rodeo in that. So I just wanted to see what that's like. So what if I was going to create something so other people could do what I was doing, so other people could develop on this chip without having this heavy HAL and this heavy SDK that's kind of awkward. And so I decided to go make CH32Fun. It's like an SDK. It's not an SDK. I guess it's kind of like an SDK, but it's not a HAL, which means it's not a hardware abstraction layer. So it has a lot of these examples, but the examples aren't showing you how do you do this in CH32Fun. They're showing you how do you do this on the hardware. So I'm not saying use my thing. I'm saying I'm teaching you how to use the hardware itself. And so I basically provide stuff like startup code, header files, a little bit of abstraction for being able to turn GPIOs on and off, things like delay and printf. But the examples themselves are almost entirely like this, where instead of showing you, oh, you set the struct value to this, and this is how this thing will configure your ADC for you, I show you every step of what happens when you want to configure the chip to do whatever it is you want to do. So that if you want to know if you can do something that's a quirky feature, you want to go push the boundaries, you want to go see something, I'm not going to get in your way. I'm not going to try to make some abstraction because I don't know what your needs are. You know what your needs are. And when you learn the underlying factors behind all of the chips and how they work, it gives you far more freedom to operate within those chips to do what it is that you want to do. Could you do all of the things that this does with a HAL? I don't think so. I think a lot of it literally would be impossible to use with a HAL. For instance, one of the things that people wanted early on was the ability to have a USB bootloader. Chip doesn't have USB, but that's not going to slow us down. We're just going to go bit bang the USB. And oh, there's this section called a bootloader, and it's got 1920 bytes. Can we make the bootloader fit inside the bootloader? So enumerate as a USB device. Make it so when you first plug it in, the person doesn't need a programmer. If you have the CH32V in your thing, and you want to be able to field program it without a programmer, just plug it into USB. It'll noodle those wires around. But how do you get that into 1920 bytes? And the answer is just by using the chip the way the chip wants to be used, instead of trying to abstract it all with a HAL. But really, the thing that started driving me had more to do with making sure my iteration times were fast, because I didn't need to think. I could just try something and try something and try something. When the iteration time is sub-second, there's nothing that just stops you from getting an intuitive understanding of what the chips are doing instead of having to wait and think and wait and think. It also makes it so that a lot of the abstractions, which you would want, or sorry, features that you would want to add that the hardware might not support, ordinarily that becomes really hard to do. Like, you're not going to be able to bit bang USB, or you can with I2C, but it'd be really slow on an Arduino library. But if you're using something where you're just turning the registers on and off, all of a sudden it becomes a lot easier to treat everything like an I2C bus and not even have to think about which pins those are on. And it also helps you find really interesting solutions for some harder problems. So going into sort of the why of why I don't like HALs, there's a really set of quotes that kind of hit me. One was one by Electromage, who literally has a thing with HALs. And the poem goes, "Oh, HAL, we're not a match. You tried to be my pal, but you make my head scratch. Your code is a puzzle, and your interface is jagged. While CPU cycles you guzzle, my interrupt runs ragged. But the hardware is elegant, you time-wasting contraption. I've discovered registers more relevant. Now I'm done with this abstraction." And a lot of times you might think about this as like, well, it looks more complicated, and it does look more complicated, but it isn't really. If you try to look under the hood, you see a bunch of complicated stuff, and it looks amazing. That is our natural first reaction. But Terry A. Davis has a comment about that. And I think his use of idiot here doesn't have to do with the intelligence of somebody, but sort of like how they choose to see these things. And he says, "An idiot admires complexity, a genius admires simplicity. For an idiot, the more complicated something is, the more he will admire it. If you make something so confusing he can't understand it, he's going to think you're a god because you've made it so complicated no one can understand it." And that's like, that's something where I think that is our initial reaction. We look at something that is hugely complicated and we marvel at the intelligence of the person who must have made it, but really that's not the best world to live in. Oliver Wendell Holmes had this quote, which was, for simplicity on this side of complexity, I wouldn't give you a fig, but for simplicity on the other side of complexity, I would give you everything that I have. And I really want this talk to be something where I can say that simplicity on the other side of complexity is possible. There are people that will say you can only move complexity around, but they are lying. They are the people that are selling you the medicine that they have made you sick with. Just let it go and believe with me for a moment that it is possible for things to be simple, both to the user and to the computer itself. So through this talk, I hope to take you guys from being technicians and bring you to become engineers, taking you from the sort of abstractions and going into crafting, from doing and bring you to understanding. So my journey in a lot of this actually started about 15 years ago. And about 10 years ago, I made this. This was my first real in-depth dive into just ripping all the abstractions out. I made a Minecraft server with the TCP/IP stack, everything else, and I put it on an ATmega 168, a kilobyte of RAM. Turns out you can run 4-player Minecraft on something that runs on 16 megahertz and a kilobyte of RAM just fine. And interestingly, that TCP/IP stack actually shipped on a commercial product too. So, I mean, it is possible. And speaking of TCP/IP, people see these things and they are afraid of them, and I was too. It took me like 2 weeks to finally like, okay, well, I guess I'll try. But it only took an afternoon to read TCP and about a week to implement it. These are things that sound scary, but they're really not. So if you get a chance, like when you're curious about something, try to go deeper. Just see what it's like to go a little bit deeper. And I'm really glad that people have been started to come with me on this. So with CH32 Fun, there's been more and more little projects that have been coming out and people using it in more and more places. it has been way more of a success than I thought. I thought I was going to release this, and it was going to be like this this other thing, CH32F042 fun, which was a complete flop. It was basically me. I made a bunch of commits over the course of a year and a half, and absolutely nobody was interested. But that's not the case this time. It has gone a lot further. And a lot of that makes me wonder, like, well, why? Why is this so different? Is it just that RISC-V is that cool? Which, yeah, it is. But not for any technical reason. It's much more social. Is it dumb luck? Or are engineers getting tired of waiting minutes for things to compile and being able to test? And are they tired of these really heavy, heavy abstractions? And they just, okay, yeah. And they just want to get back to something real. I just wanted to say, like, there are some more things that we've gone. So this started as just me wanting to make this one little processor work. That's all I cared about. But so many other people have tagged along that now we have a bunch of other chips in the series support. Things for USB high-speed, gigabit Ethernet, and actually even people have reverse engineered the official BLE stack to the point where now, like, even on chips that can't send Bluetooth, they're totally working and sending Bluetooth frames. So it's BLE frames, BLE, sorry, not Bluetooth, and it's through, we call it Isler just because we're worried about, like, you know, like trademark issues. But the point is, there's a whole community who is now getting involved in this. So being able to use a completely open stack that's not this heavy set of abstractions is not only possible, but I think a lot of people are finding it the preferred way to go. While the STM32F042 fund, that project, it was so similar. I mean, it was 50 cents instead of 12 cents, but similar micro. It even had more features like USB and more flash. But here, I guess we're just in a different era now. Like now, granted, like I think I got a boost from RISC-V and stuff like that, and the fact that it's a one-pin connection to do all of your programming, semi-host for printf and debugging over. It's still, I think that we're in an era where people are starting to catch on. I did want to make a few notes about RISC-V, and that's that I know for me, I thought it was so cool because a couple years ago I was like, well, what is the minimum amount that you need to make a RISC-V computer? Like, what can I boot Linux with? And a bunch of other people have taken my project and gone with it, but my project was to write that in a single header file. So a .h file, 500 lines of code is all it takes. 500 vanilla, no libraries, lines of code is all it takes to boot Linux. Like, it is this simple. And people were able to port that because of that simplicity to things like Scratch or Excel or Team Fortress 2, even running Linux on an Arduino, not as ridiculously as Dimitri's talk tomorrow, but being able to run these things in these places because we can find the things that are simple. Additionally, like for me, I sort of like, my motivation for that actually was seeing somebody else who wrote a RISC-V emulator that lived in a shader, which is like for drawing surfaces in video games, where it just, the colors of the pixels meant different data. And so they would have this, like this was an art installation in VR where it was just a picture on the wall, but the picture was actually ray tracing a scene using a RISC-V, a core RISC-V virtual processor. And I wanted to see it myself. So like for me, it was fun to get a tangible feeling for these things by being able to say, like, looking at the actual system RAM and what happens at boot, being able to get a feel for all of that. And that was because of the simplicity of being able to emulate a RISC-V. So some of the philosophy surrounding this is that I'm seeking zero or ultra low cost abstractions only. Like that's what I'm after. If I can get zero, I want it. I know zero is not possible. There's a whole talk by Chandler Kruth, which is really good, about why there are no zero cost abstractions. But a lot of people don't think twice about something that is more expensive, and I think you should think twice. Instead of making something where it has a complicated interface with a set of function, all this like layers, what if your interface for your API was just calling a function? What if when you needed to get a callback, it just called a function on your side? Things can actually be simple. If you want to do something in an interrupt, just do it. You don't need queues pushing things back and forth and slowing everything down. You can just do the stuff in the interrupt. Don't Don't worry about all of the fear mongering that everybody else is doing. And surprisingly, it kind of works out. Okay, that was part one of the talk. Part two of the talk is going to go even faster, and we're going to go through literally every single thing that you would need to do this. So that would be if you wanted to bring up a brand new system from nothing, and you wanted to be able to go from like C and flash it, or if you wanted to say do something weird, like I want to write some C code, but I want to compile it to go live in RAM, so I can. One of the projects I had for the Swag was I could actually like write some code, and without reflashing it, I could push my code to the Swag and test it. This is like a little conference badge. So without ever having to even push the code to the thing, except for writing a little blob to RAM, it was able to use all of the flash that was already there, and I could iterate really, really, really fast. And so this part of the talk is going to take you through every single step. So all these things are going to be online. You can go take a look at this. This is, I guess the link was at the beginning, but I can go back to that at the end. I have it up on my GitHub, all the slides to this talk. So if you do need to go back and review, do so. No time for pictures. Okay, so first part one is programming. How do you get your program onto your target device? For RISC-V, this is actually really cool because RISC-V has this sort of standard, which is these debug registers. All of these are accessible from an external interface. So you have a programmer, it's connected, it can write to any of these. You have DM data 0 and DM data 1. Those are addressable from user space, which means that you can put things like printf in there and be able to send data back and forth. If you want to be able to program the part, you go write a little tiny program, a 32-byte program, and it can go live in prog-buff. And at any point, you can say, hey, go execute that program. Maybe that program will write to RAM, maybe it'll read from RAM, maybe it'll do something to make GDB work. I don't know. But it gives you the opportunity to push the code to the device, and you can say, please execute this now. Cool part is, this seems like it's almost universal between all RISC-Vs, so it's like there's a lot of sort of like once you learn the pattern, it's applicable in a lot of places. Second part, compiler. Just use GCC. Lots of cool things going on with lots of compilers, but GCC just kind of works. Very easy to get XPack for Windows. On Linux, if you just say install whatever GCC version, there's probably a none EABI version, which is for bare metal. Versus if you see something where it's like RISC-V 32 Linux GNU, that's for if you're targeting like a Linux system. So not really what we're talking about here. What you're really after are these non-EABI, if you're looking for versions of GCC for Linux. But again, two great versions of Linux that are available cross-platform, or sorry, not Linux, great versions of GCC that are available cross-platform are by XPack and this other group by sysutils. Next part that you need to be aware of is ABIs. This is a thing from the PhD, Bjorkis, about issues with ABIs on x86. But the thing is, RISC-V, they thought about this before they went and released it to the wild. So they said, hey, here's how to use our registers. So this ABI HAL that other systems have, it's a lot simpler. So the idea is, when the computer is executing code at the lowest level, your assembly code says, take this number, put it in this register. Take this number, put it in this register. Go call this function. This will tell you what all of those registers do and how to call those functions. So for instance, if we take a look at this multiply function here, right here, A0, so actually let's back up a second. I do have to slow this part down because it is complicated. I showed you all of these registers. RISC-V has at least 16, as much as 32. And if you look, there are certain registers that are listed as function argument registers. So it means that if you want to send the first parameter into a function, put it here. Second parameter, put it here. So if we look at the assembly code output from our C code input, and you can do this in Godbolt or other resources, which you'll see one of them later. What it actually does there is that we have a function, and it takes those two input parameters, multiplies them together, and returns. And we can see where it calls, so we can see that we're going to call the multiply function here, just like this, say C equals multiply A times B. And what we notice is we actually have to wrap it in this little bit right here in order to handle calling functions inside other functions. So that's not free. That's not free. So if you think about it, maybe it makes sense to think about the trade-off between the extra runtime or inlining the functions. Most of the time size trumps, but it depends. If it's a function that's only going to get called in one place, why not inline it? The next part is memory maps. So unlike AVRs, most peripherals live inside memory space, and so they'll live there. And the idea is all of this is flat. So you can say, I make a new int star I. I have an int pointer that's pointing somewhere. It could point to peripheral, could put somewhere RAM, could point to flash. Some RISC-Vs unmap 0, 0, 0, 0. The WCH parts don't, but they do that. So if you do like, I want to say like, well, I'm going to say my object arrow X, but X is null. If you do it with unmapped, it'll actually crash, but crash in a safe way. But in WCH land, for the chips that we use, and a lot of other chips, they'll actually put the flash down here. And you have these different sections. So you have different components of your C program, from init, text, RO data, data. All of that has to live in flash, and in RAM we have data, why is it there again? BSS, heap, and stack. Heap is optional. Actually, crazily enough, only 1 or 2 people have even come by ch32fun and noticed that it doesn't have new and free, or malloc and free, which is kind of a testament, because you'd think almost everybody would use new and free. But turns out almost nobody in practice does nowadays. And that really, really makes me happy. Not that somebody couldn't implement it, but we don't even provide it, and nobody seems to care. Going over what these different memory types are, this has basically been the same since like 1979. We have init, which is code that has to run first. So that's code that has to get the processor set up. And that's doing things before C can really execute, and we'll see that later. Next one is text. That's your functions. That's your function calls. Those can live in Flash. They don't have to get copied to RAM. They can if you want, but they don't have to be. We have RO data, which is for read-only data. So if you have a const int array or something, that can live in Flash and stay in Flash. But if you have, say, like int my data equals 45 at global scope, that has to store the 45 somewhere. So it'll store the 45 in Flash and copy it over at boot. Then you have BSS, which is just like if I say an array of some data, that array will just be available to me. It'll be in RAM. We have our heap, which if you do want to use malloc and free and dynamic memory, you can, but you don't have to. And stack, which starts at the end of RAM and counts backwards. But how do we tell the compiler what to do? How do we tell the compiler where all these things are? And the answer is linker scripts. And I don't know how. I never learned this in school. I think this is crucial, and everybody should be aware of it, because it seems like magic at first. And like how does the compiler know all of this? But it's actually pretty plain and simple. This is the beginning of a linker script where we tell the compiler, you have these different memory regions. You have Flash and you have RAM. And from RAM, we can execute read or write. And from Flash, we can read or execute. It says, where does it start and how big is it? And that's enough to tell the compiler, hey, this is what exists. We also have to tell the compiler where the entry is, which is where the program starts. But I don't know, we'll see that in a minute. Next one is we have this init section that I mentioned. So this is all the stuff that has to get set up before the processor can run. This is what configures the interrupt vector and everything else. And it lives in Flash and it's at Flash, which means that it starts, the compiler has to put it in Flash, and once it's running, it'll be in Flash. Next one is text. The text region contains things like your functions. It also contains all of your constant data, and that's also in Flash, and at runtime is at Flash. The next one, or sorry, runtime is in Flash, yeah, and it's program at Flash. Next one is data. This one is kind of tricky. This is the one where we have our, like int I equals 47 or something. It has to be, the 47 has to live in Flash, but we need to be able to read and write to it. So at start, we'll go copy that into RAM, and then we will have that variable in RAM. And so that's what that says right there. I guess one other trick is with RISC-V, this is a quirk. There's this thing called a global pointer, which makes it faster for you to like reference stuff at the beginning of the RAM segment. It's just kind of like an optimization that compilers expect to have. Then we have BSS. Now this is for things like if you have an int that's not initialized, all global variables are actually started 0. Like they'll be initialized to 0 at boot. And those things live in BSS. Now, I think there's actually a bug in 003 Fun, and I noticed this when I had the slides, but I did want to put it here because that's just what we use now. I think there's a bug, but I did look, it doesn't really put it in Flash, so let's just pretend this says RAM at RAM. So yeah, don't know what's up with that. But then you have these things where you can say provide. And so this means that you could be able to say, hey, there's actually this function. Well, what if we have ROM? What if we have this other stuff? What if we are loading into RAM? We can just say provide some function name equals some address, or dot, meaning right here. So that would let you actually like write something that can live in RAM, but reference functions and arrays and other stuff in outside of what you have compiled. So now we've gone through how the compiler knows how everything fits together, and now we have startup code. This is the code that executes from the very first cycle when the processor wakes up, or I guess as soon as it is allowed to start executing code. And that's this right here. The very first instruction, at least with RISC-V, is it just starts executing it blindly. So what we do is we immediately jump to start. Start is the first function that runs. We then put our interrupt vector right here, and this tells the compiler, or tells the system, hey, if you get this interrupt, if you get a pin change interrupt, if you have DMA data coming in, if you have an ADC read, it's going to know to look here and call the appropriate function. And we'll see what this looks like in hex a little bit later. The next one is start. So that's the interrupt vector, and now our start code is here. If we're going to be running something like Linux, we actually, the first A0 is our heart ID, like in a multiprocessor system. When you wake up, all of the processors wake up. They have to know which one is which. A1 points to something called a DTB, if you're running Linux, that is. If not, those could just be whatever. I think they're uninitialized. Then we set up GP. As I mentioned, that's just a way for GCC to quickly reference things. We have to go configure some like RISC-V specific stuff, saying what mode the code should run in, and we configure the stack. Then we have to do these two other things. So remember how I said all values are initialized to 0 in C if you have a global function? Who do you think does that? Because it's not the system. Somebody's got to go do it, and it's going to be you. And so you just have to go through, and this is a little loop. I know it looks a little weird. If you know a better way to write this, please let me know, and I would gladly change the way we're doing it. Love to minimize it. But the idea is that you start at the start of the BSS data, and you go until the end of the BSS data, and you set every value to 0. Then we do that neat little tricky thing I mentioned with data, or we load the data from Flash and put it into RAM, and that's what does that copy. So all of this seems like a lot of complicated bits, but this is all that it is. There is nothing more. There's nothing more sophisticated going on here to bring all of this up. It is a little complicated, I agree, but there's no more black magic. This is where it ends. This is all there is to it. The last part is here, we have to go tell the processor where the interrupt vector is, and we say that it's an interrupt vector by setting it to 3. That's just a weird RISC-V-ism. And then we do this really neat thing where what we do is we set this value called MEPC to be main. If you guys have ever written a C program, main is the first function that runs in C. And then we mret, which means we return from an interrupt. And that's what actually gets the whole processor kicked off and everything running. And from there, you can just write C code and you're ready to rock and roll. A little bit of note about the pointers, or sorry, the interrupt vector. And that's that vector that I showed you earlier. It's just telling you where the functions are. But those are just pointers to actual code. You can write your code. You tell it it's an interrupt. That's all that says right there. And the compiler itself will handle generating all the code to go into the interrupt and return from the interrupt. So don't be afraid of writing code in interrupts. The next two parts you need to know about interrupts is that you need to know which interrupts are interrupts. And on most systems, you need some way to enable the interrupt. And the last part is just to reiterate what the interrupt vector looks like. Yes, you have the start, but we have these things where it says .word, NMI handler, .word, blah, blah, blah. The compiler will fill those in with numbers. Now, I showed you some assembly code, and you guys probably aren't used to it, But the assembly code literally maps to the machine code that you would look at if you wanted to look at it. So if you look at the very first few bytes in binary of a program you flash to a microcontroller, it's going to just be the assembly code that was at the front of start. And what that is this opcode here, where it's actually saying jump to F4. And you can see that it's actually 0F4, 000, blah, 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 6F. And that's that command. Then your interrupt vector just has literally the address in memory of where to go for each one of these different interrupts. So if you were to look at the raw binary that your processor is executing, it's just this. Next part that we need to talk about is our build system. There are tons of build systems, but you know what's a pretty good build system that drives a lot of things is Make. Who cares that it was done in 1974 or something? No, 76. I remember that because it's 9 years older than me. Only use build systems older than you. That's one of the things I've learned. So Make is actually really simple, even though it looks complicated. All it is, the whole thing, end to end, is you can set like things that you can substitute. So you can say like parameter equals something, and it'll replace this with this. And the whole principle behind Makefiles is you say, here's the thing I want. Here are the things it depends on. Here's how to do the thing that takes these things and converts it into that thing. And you just make these rules, and everything fits together. And if you say, I want to make the top thing, it'll figure out how to build it. You can even say, I want to make the top thing, and I want you to throw as many cores as you can at it. Like, so use multiprocessing. It'll figure out the dependency tree. It'll go do everything in parallel. The whole thing will just follow this rule. And I think the CH32 fun Makefile is around maybe 80 lines, maybe 100 lines. It is more complicated, but it does do a lot of stuff for you. But you can look at it, and hopefully all of it is approachable. And if you look at the Makefile for a given example in CH32 fun, this is what it looks like. So we set a bunch of parameters. This is for a really complicated example, because this one, instead of writing like a normal program, this is going to live in the bootloader, where we can override some functionality. We include the CH32 fun Makefile, and we even have this new rule called option bytes. So I can write, say, make space option bytes, and it will automatically execute this command right here, which handles reconfiguring the part to use the bootloader. There's one cute thing inside the CH32 Makefile that I did want to bring up. So I'd shown you guys what it looks like to have C code, and what it looks like to have the assembly code, and what it looks like to have the opcodes. And you can get really comfortable with this by using the topmost feature here. This file here, this LST file, for anybody who uses CH32 Fun, is always produced from any program that you make. So at any moment in time, if you want to know what's really going on, you can just open up this LST file and see what instructions the compiler has actually emitted and the processor is actually running. You don't have to wonder. It doesn't have to be a mystery. If you're making your own build system, please do this step so that when people are confused by what the heck their processor is doing, they can just go look at this file and look at the assembly and figure out what is actually happening. It also really helps people gain a deeper understanding of how what you're writing fits all together. So let's look at, there are 3 more pieces left. The first one of them is special function registers header. So one of the really nice things in C is that in modern processors that all the I/O is memory mapped. So if you want to say work with an I/O, a GPIO port, instead of having to use some weird API that creates special instructions, all you actually have to do is have a struct that defines what the hardware is, and then you can just say, hey, by the way, there's one of these structs at this magical address right here, and then you just say, oh, okay, so there's GPIOA, and it's one of these structs at that address. And then if you want to turn on a GPIO, you can say GPIOA arrow BSHR 1 arrow arrow 2. That's funny. That just means make the third one indexed bit on, and that'll turn on GPIOA 2. That one line right there. The other part about that with the special function headers that you have to think about is that a lot of times the processors, what they're doing, you can just look at this thing called a technical reference manual for almost any processor in the world, and it just tells you what it's doing. You don't have to use the HAL and wonder what it's doing under the hood. It is a book that literally says, like, oh, to use the I/O to do this, that, and the other. It literally, I don't understand how these semiconductor companies spend all this time and actually write this documentation, but they all seem to do it. And so just go spend an afternoon and just look through it. You don't even have to read it. Just page through it and just be aware of what there is. You'll notice all sorts of unusual things about the processor that you probably never knew. And it's just really kind of, I don't know. It's just worth being familiar with whatever you're trying to use and be able to understand more about it. So I talked about abstractions, reasonable abstractions, annoying abstractions, and all of that earlier. These abstractions are ones that we had spent, I don't even know, hours deliberating. So when I showed you this code, we have this nice little function that says fun digital write PC0, 1. That's a really nice way, I would like to believe at least. I would like to believe that is a nice way to turn an I/O on and off. That's also the way that Arduino does it. We spent a long time thinking hard and long about that. There's lots of interesting, weird math going on here. But all of it is written in a way that the compiler makes it all go away. And this isn't a free abstraction because somebody has to do the math, but it does it at compile time. And it's really fast because it's happening on your desktop. And now, with this nasty stuff, you're able to actually have a good abstraction that is fast and reasonable. Now, we are giving up readability of what it's really doing, but I don't know, I'd like to think that that's a reasonable abstraction. As compared to the Arduino abstraction of writing a thing to a digital port. If you go call digital write, it's going to execute, this is 2 columns here, just to be clear. It's going to execute that, and it's going to execute that to turn on or off a single GPIO pin. This is not an abstraction that brings joy, to me at least. So this is kind of what it looks like. And to be clear, when we were writing those abstractions, we were going through Compiler Explorer. If you've never played with Compiler Explorer, it's a lot of fun, where you can put your code and you can say, well, what would the computer do? What would the computer have to do to go look at that code? And it'll just show you side by side your code and the other code. How am I on? Oh boy, I think I can do it though. So why does all this matter? And the biggest thing for me is it stops this dumb rationale for mediocrity. People stop having an excuse to make things terrible because now they don't have an excuse because it just works. Bit-banging becomes completely valid. We reduce bloat and we get things like static I²C. So one of the things that are annoying is we have I²C buses. So like a master I²C bus here, it's only available on those 2 ports. And what if you want 2 of them? Also, by the way, there's 1,000 problems with I²C and clock stretching where sometimes you'll get stuck and then the device won't release it. But you can just go force clock it out, so sometimes you have to go back and forth. Why bother with all that? Just have this thing called static I²C and make every single port on your processor an I²C port. I mean, I want to feel like Jeb Bush when we do all this. The one other interesting abstraction I wanted to point out was systic. Lots of people will try to like play with systic, moving the comparator here, setting the timer there. No, it turns out it can be simple. With systics, if you just use unsigned math to say, I want this event to happen in the future at this time, I want to compare against this, it will just work. You don't need a complicated abstraction to handle your timer. It is a number. It is just a number. Does not need to be hard. Anyway, last part about this is GDB. How does GDB work? Well, you got to implement these things. You only have to implement these things, and you get GDB. And there's a bunch of projects called GDB stub. So if you Google GDB stub space your processor, if you implement these functions, it works. You can use the Visual Studio IDE to step through your code and everything else. You do have to use GDB multilib in order to use it, because GDB assumes your host's architecture. But if you use GDB multilib, it'll work with anything. And yeah, so just fun thing. Ever want to make GDB work on something? It actually is. I think Adam Feinstein, who did the swag stuff, he implemented GDB stub on the swages in literally an afternoon. It's actually pretty cool and easy. The last piece is libc. So this gives you things like memcopy, rand, stir, and all that, and printf. So there's lots of printf implementations. So for instance, if you're like on an embedded system and you want to use printf and you don't think about it, it's going to add 24 kilobytes to your executable. But there are libraries like mini printf, which is what we use in ch32 fun, which adds 652 bytes to your executable. That is a good printf right there. It may not give you floating point, but on the other hand, who cares? Just take your number, multiply it by 10, convert it to an int, and print it out. Boom! Way easier. The last part here is semi-hosting, which is printf, as I mentioned. How do you get the stuff off? Tons of people want to use serial ports. I hate serial ports. I have serial ports on my computer. I don't know which one is which. I can never find the right one. I have to set it up. It's kind of awkward. Why wouldn't I just be able to say make space monitor and be able to use the same physical pin, one pin, to printf back to the computer all the things I want to print? And the answer is on at least ch32 devices, that's really easy to do. And you get about 36 kilobytes a second of printf, which is, I don't know, that's enough for almost anyone. Oh, it's not loading. I guess we'll come back to that in a minute. I just wanted to show make clean all monitor takes about 1.6 seconds. So building the entire project for this little thing right here, this is actually doing it all with all the DMA scan out. It is drawing like the animation. This is a CH30, oh yeah, it's not gonna load. This is CH32V003 that's driving this thing up here. To reflash this from the ground up, and I mean like rebuild and reflash, is 1.6 seconds when you use CH32 Fun. So even if CH32 Fun isn't useful to you, I hope that it can stand as a testament, an approachable testament, to how you could make your own environments. And I really wanted this part of like the second half of the talk to be more about you, and that I don't want you to make your expectations and the way you think about things match somebody else's sensibilities and their intuition. You can change your own intuitions. You can learn yourself so that you match what the computer matches. And that you, when you think about these problems, you're not thinking in some abstract language. You can think about the problems the way the computer has to do it. So I hope I've been able to take some of you guys a little bit further away from being a technician, thinking like an engineer, from just applying something to crafting it. And instead of just doing, hopefully a little bit of understanding. Thank you. Nobody's coming up to kick me off now, even though I am over time. Do we want to do questions? Oh, well then, I didn't need, okay, well, okay, sure. No questions. Oh, okay, question. For CH32 Fun? Yeah. Okay, the question was what concerns do you have about building on different machines between Linux, Windows, and Mac, I'm guessing? And really the big concern originally was, number one, we take mini CH-Link, which is the tool that builds it, and we included an exe of that in the Git tree, which is ugly, but it makes it way easier for Linux or for Windows users to just go run it. And also for Windows, for several, maybe about a year, the first year and a half, we were using a sysutils version of GCC, and only recently has XPack had full support for the particular processor like line that we're trying to do. So now it's a lot easier. Now it's only the mini CH-Link thing. Like Windows users don't always have a C compiler on their system, and they certainly don't want to use it. They'd rather just be able to say mini CH-Link and get the thing done.
How do you do dynamic memory allocation?
I don't, but there are people who do, and so what I mean is there are users who use CH32 Fun, and they will just use, I can't remember the name of the library, it's like mini malloc or something, where they say like here's the beginning and the end, and it handles it for them.
The reason I use CH32 Fun is because I couldn't successfully download the Moon River compiler, and also it was scary.
That was the scary part. Was what mostly got me, and the fact that when I looked through the startup code. Oh, so actually no. What kicked me off on this entire thing, I should mention, was when I tried making a Hello World with the official SDK. It literally does a software divide in software at boot every single time to figure out a clock tick rate, which it knows at compile time. And so off the bat, it's like literally 580 bytes worth of data to divide two numbers that it doesn't need to divide in the first place. But there are a lot of people who've had varying reasons why, and it does, like if you use Mound River, you do have to run the official Chinese software on your computer, and there are some places where that's difficult. And there's also, you are right that like their website does seem to go down at oddly specific times throughout the day. I don't really understand that one. Oh, okay. The comment was that sometimes once they had to like let it wait for 12 hours and it didn't finish. I don't really know what's up with the website. They make really good chips though, so. My favorite what? Oh, CH32V003. No questions, hands down. It's not nearly as powerful as the CH32V203, which I think is my second favorite. But the 003 feels like an AVR, or like what I wanted. It feels like what I imagined AVRs would be when I was playing with AVRs like 10 years ago. So yeah, the 003 is. I was kind of hoping the new series in that they released new chips, the CH32V002, 004, and 006. And I was hoping that they would take that place, but they just didn't because they execute slower from Flash. So it was kind of a bummer there. Oh, there. Oh, I think you're going for it. Go for it.
Are there constructors in the make system? So doing initialization before the main.
Okay. The question is, are there constructors? And the answer is in C, 100% support, and in C++, 100% support. There is extra code that I think you have to say that you're doing C++. Or was the question about C constructors or C++? Okay, C constructors just work straight up. I don't remember why they work. But now I'm second guessing myself because I don't know why they work. And so now I'm getting worried. Because that's not part of the talk, and I didn't write it, but somebody said they worked, so now I want to go back and look. So I don't actually know why that works. That's a little scary. Huh. Okay. Next question. I'm going to look at that right after the talk.
I love efficiency. I hate waiting on computers. But at some point of complexity, like you can't keep it all in your head. You can't reason. It's really, really difficult to reason about everything at some level. So do you have a sense as to like at what point it's worth it that you start, adding abstractions? They exist for a reason. And also, like doing stuff from scratch for learning, for first principles is awesome, but then at some point you find yourself doing the same thing that's kind of a solved problem. So do you kind of have a philosophy or sense as to when it's to switch over? So
the first part is, where does it make sense to have the abstractions? And I think anywhere that the abstractions don't cost you an arm and a leg. And I think that, for instance, like the digital write that I showed you, I think it's perfectly fine to use digital write. But I wouldn't want to use like if the people within your chain of abstractions all have made good decisions, that's great. But I think the problem is a lot of people start cutting edges in a lot of places, and those cut edges, each one of those multiplies on each level, on each level, on each level, until whether your computer is slow as molasses or now you're getting half the frame rate you should be able to get when you're computing something on a microcontroller. And the second part was, the issue with people keeping, people with abstractions, like they're doing the same thing over and over. There are two pieces to this. One is, again, if you have good abstractions that you're basing your stuff on, then that means that's less that you have to think about. I personally don't think about what the I/O is doing when I call digital write. I don't even really think about what the hardware is doing when I say like an interrupt thing. I do operate in a higher level there. I'm aware of the lower level. It's important, I think, for you to be able to look at an abstraction to know if it's good or bad by being able to see what it's doing. But you don't have to think about what it's doing every time that you're going and calling every function. And the second part is, I think there's a lot of value to you making your own abstractions at least once somewhere in the chain, because that is something you put into a toolbox that you can keep forever. That becomes part of who you are. And now you aren't just dependent on that from wherever it would come. And I'm really just happy when I see people developing those tools for themselves, or being able to integrate sort of that into their own understanding and their own world, so they aren't dependent on insert API to go add two numbers. I mean, I don't know when they're going to kick me off here, so I don't want to call it. But go.
It's probably a simple one anyway.
Okay.
On one of the timer slides, there was a footnote where things get weirder with ARM versus, say, RISC-V. Since they're both RISC, I'm guessing ARM, they overly complicated something.
No, it's a really sad thing. When they did the ARM one, they didn't think about the overflow behavior actually automatically making sense if they extended it to 32 bits. So they just made it 24 bits. So you can't use the magic integer overflow behavior to always do the right thing every time. The comment is that you can make it work if you shift right by 8 all the time. And that is completely true, but it is so ugly. It makes me so sad. They were so close. No! But I hope does that make sense? That on ARM, not every ARM does it, but there are many ARM chips where the internal time, like the system timer is 24 bits, not 32 bits. So all of the magic, don't worry about it, you do kind of have to worry about, or you have to do what Dimitri suggested of shifting every single time you have to shift up by 8. Okay. I think that's it. Thank you so much for coming out.